we were looking at an example of a periodic Sturm-Liouville system. What we have seen is we have seen that operator, we were trying to find the eigenvalues. We found the eigenvalues and eigenfunctions corresponding to lambda is positive. So lambda equal to 0 and lambda is negative, that is lambda equal to minus mu square. We have to check whether there may be any eigenvalues in them, okay, corresponding eigenfunctions if there is any eigenvalue, okay. So we will try to see those two other cases. So start with lambda equal to 0. If lambda equal to 0, if you do, what is the equation? So equation is y double dash plus lambda y equal to 0. So basically equation becomes lambda is 0, that is why this is 0. So the general solution is y of x equal to c1x plus c2. X is between a to b, okay. Now you apply the boundary condition 1, that is y at a equal to y at b. This gives me c1a plus c2 equal to c1b plus c2. C2 cancel, so this will give me c1 has to be 0 because a and b are different. So c1 has to be 0 if you want this to be same, okay. So what is your general solution? Then the general solution becomes c2, just a constant, okay. And now clearly y dash of a equal to y dash of b, here if you apply for this general solution, this will give me 0 equal to 0, satisfied, okay. So the eigenvalue 0 is you get what is the solution? So yx equal to constant is a non-zero solution. If I choose my c2 as non-zero, that is the solution, that is actually satisfying the equation when lambda equal to 0 and the boundary conditions, okay. So choose c2 equal to 1, so is eigenfunction. So because I have a non-zero solution, eigenfunction corresponding to an eigenvalue lambda equal to 0, okay. So this is simply a constant, so which you can see from the earlier case when lambda n is equal to 4n square by pi square by b minus a whole square. When I put n equal to 0, if I include 0 here, lambda is 0, that is the second case. What happens to the eigenfunctions? When I put n equal to 0, this becomes 0, this is 0, and whatever is here, cos 2n pi by b minus a into x, when n equal to 0, this is simply 1. So I already have eigenfunctions, so I can include this lambda equal to 0 case into the earlier case by including n equal to 0. So I can make now n is from 0, 1, 2, 3 onwards. I have these are eigenfunctions, corresponding eigenvalues. These are eigenvalues and corresponding eigenfunctions are sine and cosine. But only thing is n equal to 0, lambda is 0, lambda 0 is 0, but eigenfunctions are not 2 but they are only 1. That because sine of 0, sine n equal to 0, it becomes sine 0 is 0. So this function is 0 function. We are only looking for non-zero solutions. So eigenfunction should be non-zero. So that is when you put n equal to 0 into the cosine function, this becomes 1. So I already have here, okay. So I can include this case into that. Now we have to see what happens to this lambda negative, okay, that is minus mu square which is negative. So this is the case. If you see the general equation is given, differential equation is lambda square minus mu square y equal to 0. So its general solution, again if you look for a general solution, k square minus mu square equal to 0, k equal to plus or minus mu. So you have c1 e power mu x plus c2 e power minus mu x. So this is negative, mu is always positive, okay. So that is how it is. So you apply the boundary condition y at a equal to y at b. If you apply, so you get c1 e power mu a plus c2 e power minus mu a equal to c1 e power mu b plus c2 e power minus mu b. So what you get, the equation is c1 this minus this, so you get e power mu a minus e power mu b plus c2 times e power minus mu a minus e power minus mu b equal to 0. Okay. So, this is the equation number 1. If you apply other boundary condition, other periodic boundary condition, what you get is mu into C1 e power mu a minus C2 into e power minus mu a. That is what if you differentiate and put x equal to a, which is same as mu times C1 e power mu b minus C2 e power minus mu b. So, mu you can cancel because mu is positive, so non-zero, and you get C1 e power mu a minus e power mu b, and you have a minus C2 e power minus mu a, and this when you bring it to this side, this will become plus, and you have finally minus. So, minus minus plus minus mu b equal to 0. So, this is the equation number 2. If you actually see this, if you substitute, so if you want to have a non-zero solution, okay, this 1 and 2 you rewrite, 1 and 2 actually gives me a system, or actually if you are putting as a system, you have a matrix e power mu a minus e power mu b e power minus mu a minus e power minus mu b. Similarly here e power mu a minus e power mu b minus e power minus mu a minus e power minus mu b. C1 C2 equal to 0 0. So, you want to get a non-zero solution here. To get C1 C2 non-zero solution, okay, this determinant has to be 0, that is the determinant of e power mu a minus mu b, e power mu a minus e power mu b, e power minus mu a minus e power minus mu b, this determinant minus e power minus mu b mu a, this has to be 0, okay, because it is like Ax equal to 0. To get a non-zero solution, if you are looking for, the determinant of A has to be 0. So, this is, if you, the determinant means e power mu a minus e power mu b, take it out. Similarly, e power minus mu a minus e power minus mu b, you can take it out from the second column. So, what you get is 1 1 1 minus 1, which is nothing but, this is simply, this is non-zero and this is non-zero, and what you have, the determinant is simply e power mu a minus e power mu b e power minus mu a minus e power minus mu b. But this is simply minus 1 minus 1, that is going to be minus 2. So, modulus is minus 2 minus 2. This is never be 0 for every mu positive. You can easily see, for every mu positive and a is not equal to b, this quantity is non-zero and this quantity is non-zero. So, 2 is non-zero, so it is never be 0 for any mu value. So, you do not have, this determinant is never be 0, okay. This determinant cannot be 0, this determinant is actually non-zero, since, okay, since this is actually, the determinant is this non-zero. So, you see that, that means you do not have, if mu is, if there is no non-zero solution, that means C1 C2 has to be 0. If C1 C2 both are 0, that means y of x is a 0 solution. So, completely 0 solution you will get in this case. That implies this mu equal to, this lambda equal to minus mu square for any mu positive is not an eigenvalue, okay, implies no eigenfunction. So, what you have finally, all the three cases, lambda positive, lambda equal to 0, lambda equal to minus mu square, you have eigenvalues and eigenfunctions, okay. So, you can now put it together, all the eigenfunctions were eigenvalues, first of all, I have only lambda n, which is 4 square n square pi square by b minus a whole square, Now for n is equal to 0, 1, 2, 3 onwards. Okay. Eigenfunctions are you can call them V n of x, and which are cos 2n pi by b minus a into x, and u n of x, which are sin 2n pi by b minus a into x. Again n is running from 0, 1, 2, 3 onwards. Okay. So these are your eigenvalues and eigenfunctions. They are orthogonal. Okay, and they are actually form complete orthogonal set. Complete means I can write any square integrable function or any piecewise continuous function. Okay, any piecewise continuous function, PIE, piecewise continuous function. This is actually theorem. So which we know, any piecewise continuous function fx, we take as fx, x is between a to b. Okay, any piecewise continuous function. So you can have from a to b, you can have some pieces, this kind of function. Okay, so only finite domain, that means outside if you want to see it is like it's repeated everywhere like this. So piecewise continuous function, that means you should have a jump discontinuity. It's not continuous, but it should not be, it should not have at infinity, it should not go to infinity. Okay, at these values this should be jump discontinuity, this limit should exist, should be finite. Okay, as you when you go from this side and this side, this value of the function should be finite. Okay, similarly here, so you should have here and here, that means at this point if you take the limits from this side to this side, this value should be finite. Such a piecewise continuous function I can write as in terms of as a linear combination of this. I have now running from 0 to infinity. What I have? What are the eigenfunctions? I have an arbitrary constants with these eigenfunctions cos 2n pi by b minus a into x plus bn, another set of arbitrary constants corresponding to with this for this sin 2n pi by b minus a into x. So this I can write fx in terms of this eigenfunction and this eigenfunctions. Coefficients are simply arbitrary constants. Okay, where ans and bns are arbitrary or are constants. Okay, they are constants. How to find these constants? These constants, you know, you have dot product, you can make the dot product fx with cosine with the vn's. Okay, 2n pi by b minus a into x. This you integrate, take the dot product left hand side, that will give me, here you have a to b an, okay, cos square 2n pi. So 2n pi by b minus a into x. If you actually multiply with 2m, so let us use 2m. Okay, so that you have what you have is you multiply cos 2m pi. Okay, 2m pi cos 2m pi cos square. So corresponding to n equal to m, that will be together cos square 2m pi by b minus a. Other things will be cos 2n pi by b minus a into x into cos 2m pi by b minus a into x. That integration, their dot product is 0 because n is not equal to m. Only n equal to m, that is cos square 2m pi by b minus a into x into am. This is what you get. So, and if you do for sine, you get the same thing. So you do cosine or sine, you get similar thing. So you get sine here instead of cos, you get here a bm instead of am. Okay, so this is running from including m is running from 0, 1, 2, 3 onwards. Okay, of course b 0 is 0, a 0 only will contribute. A 0 will be 0. Okay. What is the reason? Because m equal to 0, sine square, that is 0, 0 into that is 0, right, 0 divided by here also sine 0, 0 by 0, that is actually what you have is Bn anyway 0, okay, Bn into 0, whatever Bn may be arbitrary constant. So you can always write, I am simply writing corresponding to n equal to 0 to infinity for cosines, sines from 1 to infinity, and that 0 part you can write like B0 into 0. So it does not matter, B0 arbitrary is anyway 0, so symmetrical. So you can have this kind of expression. Okay. So to write it separately, so a to b fx sine 2m pi by b minus a into x equal to bm a to b. So you have now sine square 2m pi by b minus a into x dx. So you should not forget this dx. So this is what you get for m is running from. So this will give me those Fourier coefficients am equal to, you can now calculate these integrals. These integrals you can calculate, that is 1 plus cos 4m pi by b minus a into x, okay, by 2, right. This sign, once you put sign, it will become 0. Again, like earlier we have seen, cosine at a minus cosine at b, that is 0. Okay, cosine at b 4m pi by b minus a into b minus cos 4m pi by b minus a into a, that is 0. So this will not contribute. Finally what you get is am is 1 divided by, what you get is here. So this integral value is 1 by 2 integral a to b, so that is b minus a by 2. So what you get is, if you bring it to the other side, am will be 2 divided by b minus a, this integral a to b fx cosine 2m pi by b minus a into x dx. This is 1. Okay. And similarly you get bm as, again you get the same thing, instead of plus you have a minus, that is 2 sine square, right. So this is again, this will not contribute when you evaluate. So what you get is the same. So you get 2 divided by b minus a integral a to b fx sine 2m pi by b minus a into x dx. So these are your Fourier coefficients. Given a signal, time signal fx, you can have these frequencies, discrete frequencies, okay, with these amplitudes, and you can combine it. So these are actually your Fourier transforms, Given a time signal fx, you can have these Fourier coefficients, and then to get back your signal using these frequencies, using these discrete frequencies, you combine it as a Fourier series. This is what is the Fourier series. From the Fourier series, you can get back your signal based on discrete frequencies. Combine all the discrete frequencies, you can get back your Fourier series. Okay. So this is what you have seen. So now you can use anything. So what you have might see is a is 0, b equal to 2 pi is a regular Fourier series, what you see in the textbooks, okay, or 0, sometimes some others may write minus pi b equal to pi, this or this, okay. By taking this, what you get is regular Fourier series of time period 2 pi. Otherwise general Fourier series between with the period b minus a, you can have this Fourier series, okay, general Fourier series. So this is how regular periodic Sturm-Liouville system will give you your Fourier series, a regular Fourier series which you study in the engineering. So what we have seen is a regular Sturm-Liouville system also gives you some kind of Fourier series, and this periodic Sturm-Liouville system is actually giving you the series, Fourier series you studied in the in your engineering. Okay. So, what you actually study is this periodic system, periodic Sturm-Liouville system that gives the Fourier series. Now, let us see the third case, a singular Sturm-Liouville system. Okay, I will give you an example of a singular Sturm-Liouville system that for which if you find eigenvalues and eigenfunctions, you can get a Fourier series there as well. So, I will try to see the example in that third type, singular Sturm-Liouville system. Example of singular Sturm-Liouville system. I do not really do something new here, so which you already know. I just give an example of two examples of two differential equations, two differential equations which you already studied. One is Legendre equation, other one is Bessel's equation. That is what we study here in the, I will give an example here for the singular Sturm-Liouville system. So, let us take this Legendre equation, What is the Legendre equation? If you remember, 1 minus x square y double dash minus 2x y dash plus alpha into alpha plus 1 into y equal to 0. So, this is what is your Legendre equation, right. So, this is equation is defined between minus 1 to 1. And you see, you can rewrite this, put it like Ly equal to lambda y, like self adjoint form or skew symmetric form, where L is skew symmetric. If you put it in this form, what is my L? L equal to is actually 1 by minus 1 is 1 by W is 1. So, what you have is P is 1 minus x square ddx of, okay, and ddx of this whole thing. So, you have a ddx of 1 minus x square into ddx, okay, and q is 0, q is 0. So, you have there is no q here, this is your L. What is lambda? Lambda is simply alpha into alpha plus 1, okay. So, because what is PO? So, that means Px is 1 minus x square, which is actually 0 at x equal to 1 or minus 1. That means it is a singular self adjoint equation, singular Sturm-Liouville type of equation. So, boundary conditions should be, what are the boundary conditions to prescribe what are the boundary conditions to prescribe in this self adjoint singular Sturm-Liouville system when both the P of A is P at 1 and P minus 1 both are 0. Boundary condition should be y of x, or rather y at A, here y is 1, y at 1, y dash at 1 are bounded, they are finite. Similarly, y at minus 1 and y dash at minus 1 are finite. So, actually minus 1 is the smaller one. So, A is this and B is simply 1. So, these are they are finite, bounded or finite. So, you can, so these are the boundary conditions. So, you already studied when do you have your bounded solutions, it has a solutions Pn of x, these are the bounded solutions for the Legendre equation. All other solutions are series solutions which are unbounded at plus or minus 1. So, the only bounded solutions are Pn of x. That means lambda is equal to, when lambda is n into n plus 1, okay, I have a corresponding solution Pn of x which is non-zero, okay. These are the eigenvalues corresponding to this lambda. I have a non-zero solution Pn of x which is satisfying the boundary conditions, okay. So, you call this Vn of x as Pn of x and this you call is lambda n. So, these are eigenvalues and these are the corresponding eigenfunctions. There is nothing to check, okay. though lambda is positive, negative, equal to 0, all those things we have already checked, verified what are the solutions. Okay. So, your eigenvalues and eigenfunctions are these in this case. Okay. Immediately implies what is the dot product. So, you can see the dot product. So, there is no W is 1. So, the dot product is you can also write the dot product f g is actually integral -1 to 1, because the domain is from -1 to 1 f x g x bar dx. Okay. So, if for the sake of completeness you can write lambda n, so are n into n plus 1 the eigenvalues. Corresponding eigenfunctions are Vn of x, which are Pn of x eigenfunctions, corresponding to n is from 0, 1, 2, 3 and so on. Okay. But n is from 0, 1, 2, 3 onwards, you have this P0, P1, P2 and so on. Okay. What happens if I take P n equal to minus 1, if n equal to minus 1, I have still P minus 1 of x, which is also polynomial. Okay. What is this actually? This is actually, we have shown that this is actually minus 1 power 1, okay, minus 1 power minus 1 into P1 of x. We have seen P minus n of x equal to minus 1 power n into Pn of x, using this relation which we proved earlier. So, we can see that P minus 1 and P1, they are actually linearly dependent. So, corresponding to this you have same solution. So, if you think that this is your eigenvalue, okay, if n is corresponding to n equal to minus 1. So, what is that eigenvalue? A lambda minus 1, which is equal to minus 1 into 0. So, this is actually lambda 0, which you already have here. Okay. If you take lambda equal to minus 2, okay, lambda equal to minus 2. So, if you write lambda equal to minus 2. So, if you think that lambda minus 2 is also a eigenvalue, lambda minus 2, because you have a P minus 2, okay, P minus 2 is P2, so which is non-zero solution, I have eigenfunction. But I want to see whether this lambda, what is lambda minus 2? Lambda minus 2 is minus 2 into minus 2 plus 1 is 1, minus 1. This is nothing but simply 2, right, minus 2 into minus 2 plus 1. So, it is simply minus 2. So, it is 2. 2 is corresponds to lambda equal to 1. So, lambda 1. So, lambda 1 is already here, corresponding to n equal to 1. Okay. Lambda 1 is also 2. So, like this all lambda minus n's, they are already here, they are same eigenvalues. Okay. So, let us not bother about this lambda is negative natural number. If lambda is minus n, okay, if you choose n is negative values, negative integers, the eigenvalues are already here, you do not have to, they are not different from these eigenvalues, that is what I mean to say. Okay. So, you can say as a note, if since lambda n's, lambda minus n's are 0, 1, 2, 3, they are actually 0, 0, lambda 1, lambda 2 and so on. For n is from 0, 1, 2, 3 onwards. Okay. Lambda minus n, for if you choose lambda minus n, n is from 1 to 3 onwards. Okay, you can rewrite. So, so lambda n for n is from 1 to 3. So, if you consider these are nothing but lambda 0, lambda 1, lambda 2 and so on. These are here. So, you can say notes, if lambda n is this, for lambda n's, these are you should properly should write for n is from 1 to 3 onwards, lambda minus n or they are in one of these eigenvalues. Okay. So, you need not consider negative discrete numbers, so negative integers. So, you have this one. So, once you have this, if you use the properties of these eigenfunctions, self adjoint operator or skew symmetric operator, any skew symmetric, any piecewise continuous function f(x), I can write x is between minus 1 to 1, I can write in terms of this Cn Pn of x, n is from 0 to infinity, that is what I have. So, where Cn is, how do I find my Cn? You take the dot product with fx with Pn's equal to, you get Cn times Pn. All other things will be 0. Okay. So, that means Cn is, you can rewrite. So, you can write integral minus 1 to 1 fx Pn of x, these are all real valued. So, there is no bar, doesn't matter. So, divide by minus 1 to 1 Pn square of x dx. You know the value of this. This is actually 2 divided by 2n plus 1. So, you have 2n plus 1 by 2. Okay. So, this value is 2 divided by 2n plus 1. Okay. So, if P0 is 1, P0 is 1, 1 is simply 1 is 2, right. So, 2 divided by 2n plus 1 is the correct thing, I think. Integral minus 1 to 1 dx equal to 2. Okay. 1 plus 1. So, this is actually 2 divided by 2 into 0 plus 1. So, so this value is 2 divided by 2n plus 1. So, which we know. So, this is equal to 2n plus 1 divided by 2 integral minus 1 to 1 fx into Pn of x dx. This is my Cn. So, I have a Fourier series, Bessel, this is called Legendre Fourier series, and these are Fourier Legendre Fourier transform, you can say. Okay, these are Fourier transform, Legendre Fourier transform. So, given a time signal, I can make a discrete frequencies with these functions Pn's and get them. Discrete means 0, 1, 2, 3 onwards. Okay. So, I can have these frequencies and I can combine with these functions. Instead of sine and cosines, I can have these Legendre functions. I can combine them discretely. I can combine as a discrete sum. With these discrete frequencies, I can combine them as a linear combination. I can get back my signal fx. This is what is Fourier series all about. So, you can have this Legendre Fourier series if you consider this singular Sturm-Liouville system. Okay. So, why I choose here piecewise continuous function. So, if I do this, any fx I can write in terms of this sum. So, that means this sum is converging to fx, you fix any value x, that is a pointwise convergence, that is called pointwise convergence. That means this series you fix x, that converges to the corresponding fx. Okay. That series has a series of numbers, once you fix x, that series converges to fx at that point x. Okay. Once you fix x, is pointwise convergence. But there is but in all the three cases, if f of x is, that means regular Sturm-Liouville system or periodic Sturm-Liouville system or the singular Sturm-Liouville system, if fx is a square integrable function, then this fx, still I can write this fx as this sum, n is from 0 to infinity. So, for example, just for the sake of example, I can do in this case Legendre Fourier series. I can write this Pn of x where say Cn's are same here, okay, Cn's are same, but the convergence here is not pointwise, not pointwise convergence. That means this convergence means I take n is from 1 to m Cn Pn of x, okay, minus fx, okay, you integrate from minus 1 to 1, okay, this square dx equal to 0 when you take this limit m goes to this limit, it goes to 0. That means in the square integrable sense, on an average this converges to fx, okay, that is this. So this convergence is different. So if it is not pointwise convergence, but it is a square integrable convergence, it is called square integrable convergence, then this means this is same as this means not you fix your x and then see that this number series converges to that particular value, okay, is actually this meaning is this one. So this you need not worry. So that is why you learn only piecewise continuous functions, you can have this Fourier series, that is pointwise convergence, okay, but square integrable convergence, that is this one. This is the meaning of square integrable convergence. This is true even in the regular Sturm-Liouville system and periodic Sturm-Liouville system, which I missed to explain, okay, last time. So if you take square integrable function f(x), then still this Fourier series converges to that f, but in the square integrable convergence, okay. But if you take piecewise continuous function f(x), this convergence, this series is converging to f(x) pointwise, okay. We have studied Bessel equation, okay, earlier. So we can give operator as a Bessel equation operator, and we can have an example of a singular Sturm-Liouville system. Another example, that is Bessel equation, Bessel Sturm-Liouville system. So where the operator L is the Bessel type, so that we will see that example in the. So we can give one more singular Sturm-Liouville system with certain boundary conditions, okay. So we will see that in the next video. Thank you very much for watching this.